can you see like what I'm sharing?
Yeah.
Yeah. Okay.
Yeah. We can
Okay.
say it. Okay, I will
So
mute.
thank you.
Thank you.
Yeah. Thank you. So my topic for today is bridging the type system gap for circuit generators. And this project I've been calling it SCIRT. It doesn't actually make much sense. It just means Scala circuit IR tools. It's like a riff off of the CIRCT acronym. And as an introduction, most people would actually know me as Drum or Drum Forever on GitHub, Twitter, etc. And this is my blog, and you can just call me Drum as most people do on the internet, and rather real world also nowadays, like anyway. And so I'd like to start my talk by first talking about like how we think about digital circuits. For the most part, digital circuits are generally like untyped. Like if we program in C, we have int structs, etc. Chisel has all sorts of uint async data types, and we have all sorts of data types everywhere. But digital circuit in general is just untyped. It's just signal, whether it's like 2-state, 4-state, or like 9-state VHDL signals, whatever. It's just one thing, and all we have is different number of it. Like for example, an address is just a 32-bit signal. And well, this is just the most basic way of think about digital circuits, and it is not actually that true that all the digital HDLs are untyped. Like for example, in system Verilog, we have the type logic, which is a 4-state like digital bit. And in VHDL, we have STD logic vector, which is, it's just a type in the VHDL language. But at this point, we are still just thinking about one thing. It's called a bit and just a collection of them. But even at this stage, static types are in general unavoidable. For example, the next level of digital design is usually some sort of module, and we're going to put different circuit elements into a module, like this 32-bit adder that takes two 32-bit inputs and gives us 33-bit output. And most hardware description languages, such as Verilog as shown here, will to some extent check the static structure of these modules and its instantiations to make sure that they match. So we now know that actually any types would arise, and types will arise from any sort of structure that we impose on our code or on our hardware design. So structures from bottom to top, where so on the bottom we have individual wires on which we transmit logic or bit, like 4-state, 2-state, and all that. And on top of that, we build complex data out of bundles of these wires, such as bit vectors, structs, and unions. Like these are system Verilog terms. And we can also can have bidirectional bundles. And logical bit usually are just input and output, but we can also have directions like for example, in a channel in a Euro bus structure, there's a request lines going forward and response lines going backwards, and etc. And after that, the module can have multiple bundles as inputs and outputs, and after modules, we have complex connections between IP blocks. For example, there may be parameter negotiation. So not even the structure of each of those input bundles are fixed. For example, the address bits, ID bits can change. And so to describe these structures, we use hardware description languages, as have shown in several examples before. So for our purposes, we'll deal with low-level languages, and this low level it's not very clear what low level means. So I just say that we are trying to deal with some representation of the underlying graph of component wires. So we will be putting individual components onto the graph. It's just that the hardware description language gives us an easier way to parameterize what we're putting onto them. And we're just copying out modules, giving them some parameters and drawing wires between them. So there will be no high-level synthesis or no interconnects or no magical stuff like parameter negotiation and all that. And generally, what the bottom of this is usually called the Netlist, and it's usually a specially built language, and it's not really meant for manual writing, though it is still possible to write this if you do want to use some, generate some primitives or use some special blocks like RAM or I/O buffers. And some common formats include EDIF, which is not usually written by humans. Verilog, the structural subset, can be thought of as a netlist. And if you don't use those operators and variables. And there's MLIR CIRCT, the dialects HW and sequential together will make up a quite nice netlist language. Above that, we sort of have two approaches. First one is a compiler. We can compile a higher level language to a netlist. Among this, I think the cleanest example will be Clash. It is not actually that well known, but it's a Haskell-based hardware description language that will actually do a static analysis of a source program, and it is actually a modified version of the Haskell compiler GHC, and will do IR to IR transformations so that the resulting graph is actually the circuit graph. And whatever subset it chooses to support, the compiler will need to fully understand the source language. And this is static semantics, so that it knows what each part of IR means and how it corresponds to a lower level netlist. Another approach, such as a generator, is like why we're here today. Like Chisel. In Chisel, anything that works in the source language goes. In a Chisel generator, you can read files and write, even make network requests to generate the netlist. Anything that works in Scala will work in Chisel, and it's the dynamic behavior of the program, so that it's almost like a preprocessor or script that generates netlist, but it's of course much more complicated and much more structured than any, what you would usually think of as a preprocessor. The main thing I want to stress is that the high-level language program is run here. It's not being it's not the process of compiling it that generates the netlist. So the further we go on this list, we're less concerned about the static semantics of a source language. Like in a netlist, this is like the whole thing is about circuits, and in generators, like the language matters less and less. So are we losing static types along the way? Like MLIR has quite a rich set of types. Like, for example, the combinatorial operation add will it will actually not do type length expansion for adding. So it takes two 32-bit vectors and produces 1-bit vector. And this is checked very rigorously statically. But in Chisel, we're actually losing some of these dynamic checks, losing some of these static checks, and we're making them dynamic. For example, we're making a 32-bit integer literal call, and the value is 2001. However, the type itself is only uint, and it's not actually telling you that, well, this variable lit is a 32-bit integer and not like a 64-bit one. And there's actually a gap between the Scala types and the netlist type. In this case, the Chisel if it compiles to fertile, it will be missing fertile type. It's going to MLIR, it will be missing some hardware types, HW.struct, I32, etc. So what are we missing out by just not putting 32 into the type system? Well, first of all, the type loses precision. And two different uints can look the same to the programmer on the Scala side of a runtime system, and will only show up as an error after you connect them. And it will be a runtime error on the Scala side. And we also miss out earlier feedback, like as we're typing a Scala program, we won't be able to know that we are doing it wrong. We're putting a like 32 integer onto a 34-bit address bus or 39-bit address bus or something. And even though these sort of things are, if we're doing it wrong in a static type language, we generally expect some editor tooling or IDE to give us a red squiggle under the code to tell us we're doing it wrong. Another thing is type inference. So for example, it makes it like in the previous example, if you usually we expect that for type inference, if we can say that literally this literal has type uint of 32, we do not need to tell it again when we're constructing literal that it's uint of 32. It can be inferred directly. Like for example, in Rust, you can have like let a colon u32 equals 5, and you do not need to write 5 u32 again. But in Chisel, since it's more like let a colon integer equals 5 u32, and it's like we are either repeating ourselves or moving the text in a direction we don't really want it to go. So what do we need to do to fix this? A quite natural thing is to, like, what if we can parameterize the union type so that it actually knows what width it is? Like, for example, uint with a generic parameter of integer 32 and its value is 2001. It will quite neatly be translated into the MLIR code below. So, like, what kind of better types do we need? I will give a sort of prototype of this kind of system in the Scala 3, which has a significantly more advanced type system than Scala 2. It is like even mostly designed from scratch and originally even had its own name called Dotty, but it's now renamed to Scala 3. And it has a very rich macro system to match its type system capabilities and allows reflections to introspect into types and generate code at compile time. So the first thing we're going to need is singleton types. So each integer literal now is also a type if we're putting in a type position, and it's a subtype of the int type. And each literal type has its value as, if literal type is 3, 3 is its value, and 42 will not have type 3. It will have type int, but it's not 3. And there's a magic compiler function that is not a real function. It's just a compiler magic that will allow us to get this type level 3 back to the value level 3. Another thing is structural types. So if we have this is kind of like the refinement types before, but we can have a field type and we can annotate it. So to add two fields, like name is string and the value is int. And now if we put full.name here, and we also add a little bit magic, like make fields extend selectable, then we'll actually have the compiler generate code to be full.select dynamic name. And this function itself returns an any, but we already know from type is string. So the compiler will put an instance of string behind it. In these two things are what happens in a type system. And to use them, we are going to use some macros. And macros, they can override normal method calls with custom compile time behavior. For example, going back to the select dynamics thing, if a select dynamics normal function, we can only access its argument at runtime. But if it's a macro, then we can actually extract the name string at compile time, do something with it. We can inspect types. We can generate code based on what types are being passed around, and they will provide the same interface as regular methods. So if we do the error handling correctly, and we mask out the Scala compiler internals, and it will look pretty much just the same to a regular method, but it's maybe just neater or has better error messages or just does something methods just can't do. So now with this, we're going to create an EDR cell with types and which will be our circuit generator. We are going to generate MLIR code from Scala 3 using the circuit dialects, and it will be quite closely inspired by Chisel, but it's nowhere near as complete, and it won't be that easy to integrate with Chisel since like I'm not sure what the style is, but I think it hasn't been ported to Scala 3 yet. So, but this time we are going to build a circuit generator. So this is not a Scala to MLIR compiler. We will be using builders and wires, so it's actually quite like Chisel. And unlike, for example, the Haskell to circuit compiler Clash, but we'll give it more precise types. Clash was able to do it in Haskell, and here we are do it in Scala in a generator setting rather than a compiler setting. So this is what is circuit IR looks like. And up here we have a module called add32. It's a 32-bit adder. We can see that each of the lines is like an ARVM statement or instruction, but really what it's doing is just giving a graph. And on the left side of the equal sign is the output, on the right side is the input. And there's a special node called an HW output that gives some output of the entire module. And below we have a counter, which is, seg.compreg is just a normal register as you would expect. And otherwise it's quite similar. So what we want to make it look like is first we can define the types in this manner. And it actually looks quite like it will look quite like the circuit types, but it's in how do I put it? It's like written in Scala syntax, and the inputs and outputs are bounded together into a ports type, and we're going to create a module with this ports type. We can import IO.star, so it imports everything that's in this IO, so to speak, and through some macro magic, it will actually bring all of these ports into scope. And so actually output here is just a funny alias for wire, so we can assign it, and we can use A plus B like in Chisel. And this is the adder module as shown before. And this is similar by the counter module. So we're going to go through the process from the bottom up, but we're just not going to go into too much detail, but I will just show you the summary of what we have done. So we are going to build an MLIR AST, like a Scala representation of the syntax tree. The good thing about MLIR is that it's actually quite generic, and it can include very complicated parsers in the definitions, but the generic operation syntax is very usable without linking to the MLIR generator itself. Then we're going to have a module builder that will, handle the graph building task for us. Now we're going to create Scala types that correspond more precisely to circuit types, so like the bit vector types and struct types and so on. Then we'll create wire and module types like the ports type as shown earlier. So the first few parts are actually pretty boring. They are generally the same with any generator. So it's just a big AVT that with all the elements you find in the MLIR program. So if you're not familiar with Scala 3, this is basically just class or trait type, and each one is a case class that extends type. And the definition pretty will allow it's like a part of the trait type, and it implements a case for each of the integer function, etc. And this will be our pretty printer, and it will print the MLIR generic format, which is actually easier than the custom formats, but we can convert them quite easily. And now there's a builder. So each builder operation, like we're building a graph, it will belong to what I would call a context, which is usually module body. We can allocate fresh signal names and keep track of what operations we have added to this module, so we can spit out the graph later on. So this is, as expected with any other circuit generator. And now we're going to try to handle the type system part of the circuit generation in Scala. It is impossible to correspond every Scala type with a hardware type. So we actually use a type class called hardware that gives us, that tells us like if it's a hardware that has an underlying MLIR type, and we can convert it to a raw signal Y, which is the signal name, and we can construct it from the signal name that we can actually use it in a hardware generator. So, for example, for the bit vector type, like bit vector of 32 just corresponds to I32 of the in MLIR, and we can provide this an instance. Given here is like implicit in Scala 2, and summon is, I couldn't remember the name, it's called implicitly or something. But what we're doing here is basically using the type classes feature. It's just revamped a little bit. And we can give, like, the underlying type is just, built-in .i. And there's no int here will provide the value of the W parameter, and even if it's like calculated based on some other things, it's just a bit of magic I put together. It is like the const value thing I mentioned earlier. It will just take the W type like 32 and make it an integer, like the Scala value level integer. So we can preprint this underlying type. Well, preprint the underlying type of big vector of 32, it will actually just be I32. And you notice here that there is no actual runtime type tracking. The only field in the big vector of 32 is the signal name itself. And operators are not actually that complicated either. It's the same as you expect. This is how operator traits work in Scala, and it's actually quite neat. Like it allows you to give a prefix argument to a definition, like so that the operator's name will correctly overload it to these traits. So this one is a bit complicated, but really all it's doing is saying that whenever you have the context, so whenever you're inside the module and you're given two bit vectors of the same width A and B, and the add operator will give a comp.add operation into the context or into the module body and return you the result in signal name, but it's wrapped back into a bit vector. So going back to example, like what we need to do to give us an I/O value, and so that we can access the wires and wires as outputs and signals as inputs. So the wires thing, I didn't actually give the definitions here, but there's a get member that will return the underlying hardware signal name, and there's a colon equals that will assign it to a signal. And for example, the port thing above, it will have type like add 32 ports as below with 3 extra members, some A and B. And actually the I/O value will have exactly this type. And when we access the functions, we'll be able to access the wires or bit vector signals. Now we can create a sort of representation of this port type. So each of these refined structural types of ports is a subtype of ports. So we can create a trait for each of them, and we can say what types it like. I'm trying to deal with a bit of symmetry here. So I call them has if this signal is there, and you can just access it, and needs if it's wrapped behind the wire, and you actually need to assign to it, like it's a hole, and you need to be filling it. And actually, this thing cannot possibly be implemented in normal Scala code, but we can generate it using a macro, like as shown below. Here it actually gets a little bit gory, so I wouldn't go too much into the details. But we can, if we're in a macro and we have the type parameters, we can get the type representation type repr out of it, and we can look for things like refinement. So it's a structure type, but so it's a structure type thing. We're adding a field into an existing type, or an applied type. So like wire of bit factor of 32 will be an applied type applying wire to the rest, and bit factor of 32 will be applying bit factor to 32. And now we can also look for implicit or rather givens if we're talking about Scala 3 in the scope of a caller. So we have a hardware type like bit factor of 32, and we need to find the hardware instances for it so that we know what the underlying MLIR types is, and we know how to convert to and from signals. We can look it up. And we can also implement the fields in ports. And this is it's a bit weird thing to do, but as I mentioned before, if you have a type that actually extends select with marker trait, fields on selecting on it that are structural will actually go through this select dynamic method. Here we define the select dynamic method as a macro, so that we will have access to literals of, like if we pass in the field name as a literal, and we'll be accessing, we'll be able to see it as a string literal in the macro rather than a string value runtime. So if we end up putting it together, we can have, so like for each module, it has supports, like module P, or P is like a refinement of port type, like add 32 port type before, and its port member will be the will have the port type itself. So like if M is module of add 32 ports, M dot ports will be add 32 ports. Here we have like an sort of macro, like sort of definition of IO that will just extract the current module's ports for you. So now we're putting it together. We'll go through again as what happens when we create this module. So for example, for the add32 module, first we generate the module type from add32 ports. That's the inputs and outputs. Then we generate the current module's IO ports. Like, so we assign them signal names, and they will have either wires or signals given to them. Now we build the graph with MLIR operations. Like here we have an add operation, so we just add this into it. And we'll emit the module, like giving its operations and its header, so to speak. And after that, we'll actually generate a flip signature. So before we have inputs that are normal values and outputs are wire. And if we instantiate the add32 module, the inputs will turn into wires and the output will turn into normal signals. And so this is basically how things end up getting in, like SCIRT, the language I've been talking about. And so what we done? Static types, right? It's we can focus on graph building at runtime and keep track of less of the hardware types. Like for example, now bit factor doesn't need to keep track of runtime that it's a 32-bit one, because its type itself tells you it's a 32-bit one. We're not losing capabilities to generate code at runtime because we have macros. And these hardware types, like they have pretty strict types, so they end up working like normal values. You can conceivably think of like a big integer library or some cryptography library that gives you big integers with certain bit widths, and they actually work quite like those. But you can't actually print values or something. There are, of course, still circuit elements. Oops, sorry, this it's a wrong version in the slide here. What I want to say is that there will be better integration with editors and IDEs and early feedback and all that, as we mentioned before. There's still problems with static type tools, like it will make generating type generic service harder. So like if you want to generate a smarter adder, and you cannot use normal loops to go through the bits anymore, because they're in the type level. You can have some trouble trying to extract the bits. And these macros are still quite a bit too complicated to use. So like we may end up getting like weird error messages anyway when we're trying to use the macro. And it's actually quite hard to debug, like when we're doing some weird things in the type level. So thank you for listening. And this is just sort of prototype, but you can play with the code on the link I have given here. And thank you for that. That's my talk today.